Hello, everybody, and welcome. I am Christian Malaga from Imperial College London, and we are very fortunate to have today with us Professor Shiling from the Colorado School of Mines. And I'm just going to introduce the speaker to us. This is a second webinar. And as I said, we are very, very honored to have Ling with us, connecting from New Zealand. Just a reminder, you are welcome to pose your questions, to write your questions using the Q&A facility of the Zoom interface, and we will be answering the questions. We will be collecting them and answering them at the end of the presentation. I'm going to proceed to present Dr. Shiling now. So he received his PhD in civil engineering from Colorado State University, and then joined the Faculty of Civil and Environmental Engineering at Colorado School of Mines in the fall of 2013. Before that, he worked as an assistant professor at South Dakota State University, and his research focused on multi-hazard mitigation through performance-based engineering, numerical modeling of structural dynamic behavior, traditional and innovative timber systems, and large-scale dynamic testing. Very large scale, to be sure. Ling received the 2012 ASC Raymond Rees Research Prize for his work on seismic performance of mid-rise wood frame buildings. And he is the author of the Seismic Analysis Package of Wood Frame Structures, SAPwood. I'm sure many of us have used that. And he has participated in the NSF-funded Nicewood project and served as one of the lead researchers in the shaking table test of a full-scale 7-story wood steel hybrid building at Japan's Idefeng shaking table. But today, he's going to be speaking about another, even taller specimen. The title of his presentation is Shaking Things Up, the Journey Towards Testing a Full-Scale 10-Story Wood Building. So with that introduction, the screen is yours, Ling.
Thanks, Christian. Thanks everybody for your time and attending this seminar. I'm gonna start sharing my slides. Christian, can you see everything okay?
Yes, I confirm everything is good.
Okay, I'm gonna, nice to meet everybody, but I'm gonna stop my video so that my playback quality is a little bit better. All right, so as you see the title, like Christian just said, today we're going to talk about the 10-story test we just did last year in 2023. But today I'm going to actually share with you a little bit about the history behind all this. It is a journey towards how we get there to test this wood building and why we're doing it. So every journey has a starting point, right? If you are following the wood research, or specifically wood seismic research in the US, you know, it has a beginning. In fact, if you look at all the seismic wood papers, you will not be able to find too much before the 1994 Northridge earthquake. But after that, because of the enormous damage the earthquake had on wood frame structures, a project called the Curie Caltech Wood Frame Project, right after the Northridge earthquake, which was funded through actually some FEMA money from hazard prevention, started to look at light frame wood structures, which in the US typically people call them 2x4 construction. So they start to look at the wall tests and some small scale building tests, like a 2-story, I believe this one's in Berkeley. Then to understand like how does those existing wood system perform in earthquakes, and also develop numerical tools to actually study it. This type of project, there's multiple universities involved, and it runs from 1995 to almost 2005. It took a lot of time to get everything out. So that's where wood buildings as a subject in earthquakes was start to being taken seriously in the U.S. But I didn't, get to do that. This journey is also quite a personal journey. Where am I? Back in 1995, I'm still in China. I'm a middle school student, but I came to the United States in 2003 because my background was in actually bridge engineering in China. So I have no idea what wood building is. So you got to start somewhere. So we started by building small wood buildings. You can see me and another student, a carpenter, building like some stuck walls. At Colorado State University, we have a small shake table, so we're still starting to do some mostly one story. Yeah, because you see the height of the ceiling. One story test. And I started to develop numerical tools. All that happened during my PhD years and postdoc years. So we, building on the research result from the Curie-Caltech wood frame project, we reached 2009. That is when we are able to do the test Christian just mentioned. It's a Niswood test. It's a 7-story hybrid. So first story is a steel frame, and then 6-story of light frame wood. That is actually the tallest wood frame buildings by U.S. building code that you can build. So let's play it. You can see this room we decorated. That is actually the room here on the corner on the roof. You see, those are the steel plates that are serve as seismic mass. And this is a 3D test. So you see the vertical motion came first. And on the left, you see that's Professor John Vanderlyn. That's my advisor. Yeah, that's a picture. I especially used the picture when he was younger, and so that's when we did the test. So after this is done, we basically proved that through performance-based design, this building was actually designed using displacement-based design. You can make a tall light frame wood building at least resistant to earthquake. We still see some damage, but this is already like I said, the tallest allowed by the code. Then what's next? In fact, during that time, around 2009, 2010, mass timber was already a big thing in Europe. In fact, in London, where most of you are, there's already a 8-story CLT building coming up. And in Italy, Professor Ariel Sicoli has already been testing, actually it's the same year, a 7-story CLT building at E-Defense from one of the Sophie project. And also, yeah, this talk, if you haven't seen it, it's great. It's a TED talk by Michael Green, which actually introduced me to the perspective of mass timber. Why we should build wooden skyscrapers. So the potential, we can build taller now. So around that time, Canadians are definitely the first developer, first adopter of mass timber in North America for apparent reasons. I mean, it's Canada, right? They want to sell more wood. So in fact, while we're testing the 6-story building in Japan, FP Innovations, back then they're called Foreign Tech, if people still remember. They have been testing some CLT shear walls. Okay, they got the testing result and then they want someone to model it for their new book, which is called CLT Handbook. A lot of people now know that. John and I were invited to participate in chapter 4, which is the lateral design chapter of the CLT Handbook. So what I did is that I used Sapwood and I did a little, simplified model based on connector mechanics. And then we did a redesign of the Nicewood building using CLT rocking wall, a CLT shear wall with a R of with the assumed R value. So this study went into the CLT handbook, and then eventually we published some papers. It became the basis of current CLT shear wall seismic design factors in Canada. After we did that work, so that's 2011, about 12, we're start thinking about how we can introduce mass timber construction into the US. So by 2014, a group of industry collaborators, apparently you see Arab here, there's much more. We had a workshop focusing on CLT in seismic regions of the United States. So this workshop, it is actually, if I look at it right, it is actually the first ever workshop on mass timber building in the United States. So there are a lot of industry folks and manufacturers joined in, and we had an opinion paper, which happens to be the second highest cited paper of myself. It's basically in this paper we said we're gonna try to strive for developing a new type of tall buildings in seismic region using mass timber that is earthquake seismic resilient. So that led to the proposal to National Science Foundation around 2015 to do Narrow Tall Wood project. The Narrow Tall Wood project, the full name is Developing Resiliency-Based Seismic Design Methodology for Tall Wood Buildings. So we did in like 3 parts. We look at the architectural archetypes for this type of building. We decided it would be a open floor plan, beam and column grid type of building, because for commercial use, for the most part, with some sort of lateral system as the core. Then we look at small scale testing, and then eventually we want to do a full scale test of a tall wood building on the UCSD outdoor shake table. Back then, when we did the proposal, the shake table was still 1D, but fortunately for us, it was upgraded to 3D about 2 years ago. So our test is actually one of the first who utilized that facility in 3D. But let's step back and see, why do we propose resilience? Because in the Nicewood project 6-story, we know we can make the building pretty resistant to earthquake. Resilience is really intended because it has brought you some other benefit. A good example is Christchurch earthquakes, which it's ironic, what a small world. I'm actually doing this presentation to you right here in Christchurch. We'll know about it. It's not a very huge earthquake, but it damaged a lot of buildings in downtown Christchurch. If you look at the before and after earthquake shot in the Google Street View, you see, for some reason, after a huge earthquake, even though a lot of buildings are modern buildings, they built to the building code of a developed country, which is New Zealand, the buildings, they disappear. You compare the number of casualty of building to people, although any casualty is too much, but if you look at the ratio, you see our building code is actually doing something that we intend them to do, which is protecting life safety. But you would not have a building to go back to, because to dissipate energy, you need ductility. For traditional lateral system, ductility was developed by either yield of the steel frame, or cracking of concrete, then you are allowed to have residual drift, both of which are very hard to repair afterwards. You have to demolish the building. The resiliency concept is actually to achieve this. We have some good development happening along the way as we speak, because in fact it is where I'm teaching temporary right now. University of Canterbury, a group of researchers led by Andy Buchanan for the most part, start to experimenting post-tensioning on wood, okay, around even 2005. So they did a lot of testing. They look at the post-tension, the moment frame wood, and also some rocking walls. Then we pick it up and say, okay, that seems like to be a good idea, because at that moment in Canada, they already been building 18-story buildings out of mass timber, but they're using concrete core. This is the picture right here. This is Brook Commons in UBC. So we're thinking, okay, can we replace concrete core, which we know is going to crack and have residual drift during a large earthquake, with a rocking wall system? To do that, we need to actually test some rocking wall system ourselves. Because the early testing done at University of Canterbury, most of them, they push it to 3% drift about. We need to actually push it further to know all the damage modes. So we did a test around 2015 at Washington State University, where we pushed the rocking wall to about 10% drift. And we observed a lot of damage, mostly concentrated at the rocking toe. This was an effort led by my co-PI. Now, Dan's already retired, but he did a really good work on this. There's a paper here if you're interested. Then once we know about the behavior of those walls up to 10%, we have the confidence to actually put them in a building and test it. In 2017, we start to test a small 2-story building, but by that time, it's already the largest mass timber rocking wall building ever tested. Of course, you have taller ones back at Edifence in Italy, but that one's just a platform CLT shear wall. In this test, the main idea is to see how this coupled rocking wall system fare around earthquakes. The result is actually pretty good. We did a total of 14 tests. We saw no damage. In fact, what I'm going to show you is a public test where we run Northridge earthquake back to back because we know it won't get damaged. Yeah, so that's the first Northridge earthquake. Yeah, then the second one. So what we found out is that a system like this, you can actually run this type of earthquake Northridge at the design level all day long. It will not get damaged. So we pushed a little bit further. This one we actually did a MC level earthquake and above and beyond, and then we pushed the building to 5% drift. This is some details of the second floor. You can see how the wall and the floor, how they interact. And this is the rocking toe, which is at the bottom corner of the rocking wall. You can see it rocks. So we found out both the rocking wall and the beam and column mass timber system can actually be very resilient. But the question is that can we scale it up? So it's time to move on to the 10-story test. Oh, but yeah, this happens. It actually the project originally was planned to be from 2016 to 2020, but COVID happened. It now thinking backwards might be a blessing in disguise because it actually gave me a good about 2 years window to refine the design, sharpen the pencil, and also fundraise for the project. But then back 2020, over those 2 years, everybody getting shut down at home. We did a lot of designing and detailing and contracting and then fundraising. So by 2022, we got this building designed. It is designed to Seattle hazard. And then it was designed to satisfy a resilient performance target where we don't want any residual drift whatsoever, even after MCE. The building can have some repairable damage at MCE, but no damage under DBE. We also focus on non-structural system because if you're talking about resiliency, you need to care about non-structural system. They actually account for most of the downtime for a earthquake, for any earthquakes. So we are looking at quick repairs on those systems. The building itself is a full-scale 10-story, and you can see it is supported laterally by 4 rocking walls, 2 pairs. In this direction, we have the CLT rocking wall, and in the other direction, we have the MPP, which stands for Mass Plywood Panel Rocking Wall. We showcase those just so that we can show that the design methodology works for any mass timber material. Then this is the elevation. We got every construction package ready, and then we start to get donations. So we get the rocking walls from different companies. Then we have floors. In fact, the first 4 floors are actually from Europe, but it's donated by a Canadian company. Then we have NLT, DLT. If you study mass timber, you know what that is. And then finally, we have a plywood product. We call it veneer laminated timber from Boise Cascade for the top 4 floors, as well as the beams and columns. So beams and columns, typically you see glulam, but in this building, it's not glulam. It's like a LVL type of material. Finally, every connector is from Simpson Strong Tie. The rocking wall, which is apparently the center of attention, you can see this is very similar to the 2-story version. The shear transfer from the wall to the floor are done by this slotted hole, so that this rocking wall is only a lateral system. The rocking wall itself is about 35 meters tall. So we have to ship them in 3 pieces and then stitch them together in the middle. The PT is on the outside, so 2 PT on each side. And then they're only attached from the bottom to the very top. So there's no intermediate anchor. It is a single panel shear wall. The construction of the building, as similar to all the mass timber construction, it is very fast. A total of 5 months to build everything structurally. But that's even including 1.5 months we're waiting for some parts. So like about 3.5 months to build a 10-story building. We still have some finishing work for the non-structural systems. But let me first show you this so that you get a scale of the structure. This is 2 workers putting in the final panel on the roof. So this is topping off. But as you can see, the building hasn't been PT down yet. So there's some temporary bracing. If you ever visit UC San Diego outdoor shake table, it's in kind of a little bit inland of San Diego in the Miramar area. This is a view. The two red tower are the safety towers. They need to be there to protect the control building, which you will see once we zoom out. The control building is where they house all the hydraulics for the shake table. Yeah, they thought they have a 6-story tall safety tower would be enough, but yeah, apparently the building is taller than that. And you can also see the shake table right here. The structural framing, once it's completed, we start to add on non-structural system, which including exterior facade on the bottom 3-story of the structure, except for the glass curtain wall, we only did a 2-story. Those are all donated. Yeah, a lot of people ask why not the whole building. I mean, first, we're out of time. Secondly, we're out of money. Third, for the no damage detail, we're gonna put in a 3-story. It'll tell us a lot about it. We also have stairs and the interior walls, some of them. Then we need to instrument the building, of course. This is likely the most instrumented building specimen ever for more than 750 channel of data, including axometers, displacement gauges, string gauges, tilt meters, load cells. Everything has to be checked. And it took about 3 months to prepare all that. And just so that you know, if you plug in 700 channel of data into the DAC, this is what it look like. And also a lot of people ask, why don't you use wireless? For the density of the instrumentation on this building, as well as the dynamic nature of the test, really the only reliable way to get data that is fully synced is by hardwire them. UCSD has a lot of other research facility, like they have a drone lab where what they call, they do LiDAR scans of actually buildings and roads. So they actually was able to do this 3 LiDAR scan, point cloud for our building for us for free. So now this data is there, although the building is not there anymore because we downward testing, it's been deconstructed. But later, if we want to go back and check on, is that nail really there? We can actually go to the point cloud and walk through it. So after everything's ready, you talk about testing. So in fact, it took a year to do a preparation. So by the time we're ready to test, it's 2023 now. Because we designed this building to be resilient, we know we're going to do a lot of tests on it. We scale our ground motion suite to the Seattle record. And initially I was thinking, okay, well, maybe just to give you an idea, the NISU test we did in Japan, we run 5 tests. Okay. The 2-story test, we run 14. So this one we think, okay, well, maybe we'll run 30. But it turns out that the building performs so well that we end up running 88 tests. So 88 tests, this is a little bit busy table, but you can see the peak ground acceleration PGA here. You can see the progression. Then this is the hazard level, which you have up to the 475 year, which is design level, then all the way to MCE. We run multiple MCEs. And then our collaborators at University of Washington also want to see a different source mechanism of earthquake, so we run different earthquake sources. So all in all, we run all these to collect data. The earthquake, if you really build a building in Seattle and wait for 10,000 years, you'll see this much earthquake. So this is one of the largest tests we did. It's an MCE level earthquake. I'll play it. And then, yeah, this view is at a rocking wall on the other side. We don't see, but you see this door open. And this is a cool view. That is a drone on the top of the building looking down like a plan view. Yeah, one immediate thing you notice that the building actually exhibit a lot of higher mode response at the beginning. Because the views I just showed you, we have to zoom out so much. So there's another view focusing on non-structural systems, specifically on a balloon framed facade. That is on one corner of the building. You'll see how this behaves, because this view is a GoPro camera at the corner. By looking at the non-structural system and how they actually return to its original position, it gives you a visual proof that the building actually, the structural system recenter. So looking at data, we look at, as all the seismic testing, we look at first and foremost interstory drift. Typically, when you only run like one or two tests, I'm gonna show you a time history, but here, because we run so many tests at different intensity levels, we're actually be able to show you a distribution of the maximum story drift, just like what you will get from a numerical simulation, but this is experimental. So you can see at MCE, we're reaching about 2% drift. And you look at acceleration, also the maximum acceleration is around between 1.5 to 2 G at some stories. And it's interesting that if you look at where those maximum responses are, they are never at the bottom stories. This is very distinct because for low-rise building, you always have the maximum drift at the first couple stories. But everything for this tall building is happening at the top. And then if you look at the acceleration, you can see the higher mode effect, right? You can see the middle and nothing here, then the roof. This is another earthquake. Okay, it's a Chichi earthquake. It's a design level event. This is to show you what would it feels if you're on this building during a design level earthquake on the 10th story. So yeah, this is the top floor. If you still remember that that shake we did at the beginning of this presentation, you see the difference. This building, the acceleration is really not that much under design level earthquake. But you still see the entire building rocking, gravity frame, and also rocking wall. And also, yeah, this is a 3D motion too. So yeah, you can see our tables, and yeah, even some marks are still there, and our stuffed animals. So after 88 earthquakes, we see some damage, yeah, but only on the non-structural components. There's no structural damage that is visible. There's no residual drift. In fact, after even more earthquake shakes, we are able to deconstruct the building. We look at the rocking toe. Remember the WSU test we did? We pushed the wall where the toe get crushed. We have this armor plate protection, and then the toe, in this test, not crushed even after repetitive earthquakes. The conclusion is that the resilient tall mass timber building is not only viable, it is also practical. We think mass timber rocking wall is the key to do that. The gravity system and non-structural system can all be designed and detailed to be very robust against repetitive earthquakes. We have a paper under review right now. I think this one's gonna come out this summer at the Journal of Structural Engineering. When you have a very resilient building, you don't just do 88 test, okay? So after the 88 test I just presented, there's another payload test we hosted for Michigan Tech from NSF, where they tested some friction dampers. They did another 19 test. Then the building was handed to our Japanese collaborator, Sumitomo Forestry. They reconfigured the rocking wall. They put bigger rods and a proprietary energy dissipator, did another 51 test. Then we took the top 4-story down, turned the 10-story into a 6-story building. And then we handed it over to Oregon State University research team, where they did another 3 phases of testing with 3 different lateral systems, a total of 86 tests. All that, 244 earthquakes total for, if you just look at the bottom 6-story. There's no damage. There's no residual drift. This is likely the world's most resilient and most shaken full-scale building. But should we be really that surprised? Right now I'm in Christchurch, so I'm gonna actually after 2 weeks I'm going to Japan in Kyoto, which is very close to this building you see on the picture. This is the Todaiji Temple in Nara, Japan, which was built. The most recent rebuild was more than 300 years ago, and it is actually taller than the tallest full-scale building ever tested to date. So I think we still have a lot to catch up to do, and then there's a huge room for tall wood buildings to play a role in our resilient new cities in seismic regions. To summarize, I told you it's going to be a personal story about this journey that brings us to today. It's personally, I feel it's kind of awesome. It took a long time. You see my kids. No, they used to be primary school, and now they're high schoolers. I'm very grateful for all the collaborators, sponsors, and friends that we met along the way, and we're just getting started because as we speak, we're working on a P695 project, which we will eventually try to put the mass timber rocking wall lateral system into ASC 7, which is the US code. So with that, I'd like to thank everybody for your attention. And if you want to contact me, there's my Twitter, my email. In fact, if you go to my Twitter, I use that as a building log when I do this project. So if you look at my Twitter timeline, during 2022 to 23, you'll see the building process of the entire building. I post, a lot of footage, and also the sponsors, especially National Science Foundation and U.S. Forest Service. Without them, this cannot be done. With that, I'd like to open it up for questions. No videos. I'll turn my camera back, and so Christian, we'll take some questions.
Thank you very much. Thank you very much, Link. Fantastic presentation. Very, very informative and impressive. So we have received a few questions online. I'm just going to read a few of them. The first one is about guidance and research for joints in wood frame structures. Maybe you can offer some comments about that.
Yes, there are two type of joints in this building. There's two type of unique joints in this building. One is displacement or drift compatible connections, which was designed by my good friend Steve Pryor from Simpson Strong Tie, where the connections are designed so that they can rotate freely during earthquake to accommodate drift up to 5% drift actually. The reason we need to do that is because we know this building unlike any other building, they might see one or two earthquakes in their lifetime. This building will see hundreds of earthquakes. So we need to make sure that those connections, they will not get damaged during repetitive movement. So there's one that I wouldn't say it's guidance. It's just something that we take into heart, that we detail the connections for. Another type is what I call overstrength protected connections, where they are, on the other hand, they need to be like really rigid. In fact, you see them right here. The connection between the wall panels, they're supposed to be very rigid. They're designed actually by taking the numerical simulation we did under MCE. We look at the maximum moment on the wall, or either that, or we use the sweet mean times 1.3 to design those overstrength protected building at the MCE level so that they remain elastic. That applies to this connection and also all the shear transfer mechanisms. We don't want them to get damaged or get loose during repetitive shake. So those are two kind of guidelines for us to do connection design for this building. Yeah.
Thank you very much. Thank you. The next question is about defects and imperfections. So how is it possible to ensure that such a large structure is completely free of minor defects? I guess it's not free of minor defects, but and particularly when using natural materials as timber. So maybe you can comment about.
In fact, the reason this building is free of defects is because we actually use exclusively engineered wood product, which is not just a solid timber column where you could have a big knots. Then you're, then that's a big problem. But all the columns and beams and all the panels in this building, they are made from wood plies. They glue together. Then each ply, yes, they might have defects and everything, but when you glue them together, it goes away. It's a perfect property for engineered wood product. It works for LVL. It works for glue lam. It works for CLT. It also works for MPP. So yeah, one main reason for use engineered wood products instead of a solid sawn lumber. First, you don't have trees that big anymore. Secondly, is to average out the defects so that the entire thing on average is defect free. We can assure that. We can assure that because because of quality control in the engineering product.
Shanti is asking what is the maximum lateral displacement that you got, and how did life loads were at different levels were taken into account?
The maximum displacement we got overall the building, I think we during the MCE level I showed you on the drift, we reached about 2.5% drift. The building is designed based on performance-based seismic design, but it's also because we have a lot of industry collaborators. We want to make sure this building can actually be built per U.S. code. U.S. code actually have a hard limit on seismic induced drift. That is like about 2%. So I think we met that pretty well. The question about the live load, or maybe there's going to be some question about supplemental dead load on the building. is that first of all, the building, when you're doing a dynamic test, even at a full scale, because we have a reduced floor plan size because of earthquake or because of shake table dimension, you have the choice of either you try to mimic the building's a real 10-story wood building's natural period, or you want to mimic its real weight. Once we did the building, did the design, we built it up, we found out that the building natural period is already close to 2 seconds, which is pretty close to a real full size 10-story wood building with all the supplemental dead weight. So we didn't add in any more supplemental dead weight, because if we do that, this building with this floor plan, you're gonna look at a 4-second natural period, which is unrealistic. So we did not put a supplemental dead weight or live load on the building because of that reason, is to more honestly reflect the dynamic property of a tall structure like that at a full scale and full size. So yeah.
Yeah, thank you very much. I believe that also answers the questions of Colin.
Yeah, I know that one's gonna come up. It's a popular one.
So Ian Smith asks, how was the out-of-plane integrity of the wood shear panel achieved? The composite glue between laminations only?
Yes. The out-of-plane, yeah, the cross-laminate timber, I guess that's what you're talking about. There are two type of walls, right? Like I said, the MPP mass plywood panel is just like plywood, and then you just glue plywood up to about 10 inches thick. The CLT is a 9-ply CLT, which is about 310 millimeters thick. Yeah, everything's by glue for material itself. The wall itself, out of plane, we have braces at each floor to brace them so that they don't fall out of plane. But for material, yeah, out of plane is purely just glue. Yeah.
Yes. Shanti is asking if you it will be great if you share the details. I think publications are coming now. Luca asks, first, they thank you for the presentation, and if you could expand of any effect of the inertial force due to the loading regime was considered. I guess that.
Yeah, I don't quite get get what you're asking. The loading, like I said, is a Seattle record, and in ASC 7, which is the US seismic design code, if you pick a location, you can actually get a response spectrum. Then it'll give you the design level, it'll give you the maximum considered earthquake level. Then we just take our ground motions and we scale them up to that level. Because we design it for Seattle, then we test it for Seattle. Yeah, Seattle has another great property is that it truly have different mechanism of earthquake, including crossed earthquake and the subduction zone earthquake and all that. So it's pretty nice. Yeah, hope that answers the question, but I'm not too sure.
Ian Smith from Atkins Realis is also asking if, despite the connection over strength, there was any damage observed in the connections.
There is some damage to the non-structural to the building connections. For example, the facade I showed you that move back and forth. Some of the clips they somehow they're supposed to slide, but they catch. Once they catch, they get ripped off. But there's really no structural connection damage. There's some damage we observed on non-structural to structural. There's some damage we look at on the stair handrails. The stair system actually performed perfectly. The handrail, sometimes they get caught. Yeah, the only damage in connections we see in this building after so many earthquakes is really when a non-structural connection get caught, that they're supposed to move, but they can't move, then they get ripped off. But that's it. We would, I mean, you see all the glass windows on this building. We didn't even break a single window, which is amazing.
Yeah, yeah, amazing. So we have a good number of questions that reflects the interest on your talk, Ling. The next one is by Antonios Katsamacas. First, they are thanking you for the interesting presentation. And then the question is, in the two-story building test, did you use some devices that look like U-shaped steel dampers to connect the adjacent rocking walls? Did you also use the devices in the 10-story test? I mean, were the same? Could you please elaborate on that?
Oh yes. Let me just show you. That's called UFPs. I mean, it's not our invention. Concrete people do that already in their rocking walls. The UFP in the 10-story building, you can see them like right here. Yeah, because for two-story building, we actually do coupled walls because we have the space. We can couple two walls. For 10-story building, because the wall itself is already very wide, so the only place we can put them is between the wall and what we call bonding columns. So they serve as energy dissipation. In fact, in our design methodology that we developed, for this type of system to have enough inelastic energy dissipation, we require at least 25% of the strength coming from these yieldable elements. So.
Thank you. Simon Don asks, is it possible to use dimensional analysis to carry out a smaller scale test, or does work such as these have to be full scale?
Well, it depends on what you're looking for. If you're just looking at one aspect of the test, it's possible. Dimensional analysis, we know even for steel and concrete, when you scale things down, especially you're conducting a seismic test, you are sacrificing something because you gotta match one non-dimensional property. Then you have a lot of choice. One dilemma is always, even if you're doing steel structure, is the inertia is hard because if you really follow everything, you have to find a material which has the density, mass density that's huge if you want to test it small. For wood, you have another layer of complexity where is the connection. It's very hard to, not very hard. It is impossible to scale down the wood fiber. And then the connection, either you use screw or nail, their strength and stiffness characteristics is directly tied to their interaction with the wood fiber. If you cannot scale down wood fiber, you cannot scale down connection. And if you cannot scale down connection, you can't do much for wood buildings. That's why for most of my research, the wood building, we have to test them at full scale. For tests like that, it's a lot of work, a lot of money, a lot of effort, but by the end of the day, it's all worth it because it actually help clarify a lot of things with certainty, rather than try to relay back to some model that are not 100% capturing the reality. But it's doable. If I want to just look at the rocking wall as like a geometric study or sensitivity on rocking wall aspect ratio, yeah, I believe a scale test will help. But for a test that I'm actually asking people to donate, and a lot of industry partners, yeah, they want the real thing. So,
Thank you. Luke asks, have you perhaps measured moisture content on the timber elements? Have you speculated what impact would higher moisture content have on the study? It was raining.
Yeah, that's very good questions. Yes, yes and no. I don't need to measure it because during our construction, we experienced the wettest winter in San Diego. For like weeks and weeks, the building is just drenched in the rain. So I don't need to do a measurement to know that the building, the moisture content is greater than 20% for sure. Because at one point there's pool of water on my floor. Does it? In fact, you can see the building is very beautiful when we start constructing it. But yeah, just look at those wall panels, but just look at this. Yeah. So but this also actually worked out pretty well because we actually have the worst case scenario. We didn't do any water protection. It is super wet. Everything's pulling water. And even when we are about to test, there's rains like all day. So you could assume everything's wet use. And then the building still performs very, very well. My personal story is that I didn't present it here. I also did some study moisture monitoring on real buildings. There's a building in Portland called Carbon 12 where we went and installed the wireless moisture sensors to see how it dry out. Once you have a building and once it's enclosed, it dry out pretty steadily. That Carbon 12 building is also, when they constructed, is the wettest year in Portland for the last 50 years. And for some reason I just run into those extreme situations. But the building is fine. I don't believe the moisture has any negative impact of scale to what we want to accomplish in this building. So if you really just test say a nail or screw connection and do moisture, you'll see the difference, right? But for a actual building design, I think there's enough redundancy there to actually absorb the impact of moisture during construction. And once you enclose it, it dries out, then it should be fine.
Thank you. So just to, Shanthi, thanks you for a very interesting presentation. And Ian Smith from Atkin Realis also thanks you for a brilliant presentation. He also asked, in reference to the dead life load ratio, understood that it matching the natural period of other structures is done, and that's understood. But does this mean that we are talking only about the use for dwellings and light office rather than more heavily live loaded use?
Okay, that's two things. The amount of mass we put on the building during the test is actually different than when we design the building. Because if we were really just designed for what we tested, the loads, the building columns and beams would be much smaller. But when we actually design the building, we do design it using a recommended office. I think it's a heavy office. Don't quote me on that, but it's in my paper. 50 or 70 PSF supplemental live and dead, and so basically when we start designing the building for gravity purposes and also for the wall, we actually just collaborated with our industry collaborator, in this case KPFF, to design it just like an office building. So I would say it's definitely not a light version. It's definitely a normal version. Another reason we actually designed this to a normal gravity load is because we want the beams and column sizes to be representative. We even did a fire design so that we have actual sacrificial layers, so that if you want to expose your beams and columns, you can. So the beams and columns, they're actually full size. The reason that is important is because I mentioned that there's flexible joints where the beam gonna rotate. Once you do rotation, you need that cross-section to be actually of full size so that you can actually mimic the real situation in a real building. So to answer that question, the building gravity design is done on a normal loading with dead load, supplemental office, typical office live load. It is when we actually do the test, we decided not to add more load because of lateral period.
Thank you. And Colin asks about the no structural damage, only some connectors in some non-structural aspects, whether you would put that down to the flexibility of wood.
Yeah, there's some flexibility of wood involved, but more likely it is because of clever detailing. I mean, it's not in this presentation, but I can talk a little bit about. For example, we have 4 corners. They are 4 different facade. You see the performance of that one. I mean, you can see very clearly how it avoid damage by sliding. The others are not like that, but we always have some like sliding tracks or some displacement absorbing mechanisms in the non-structural detailing, so that they don't get damaged. As for stairs, the stair landing is actually isolated. So the way we did this is that the structural design, we did the simulation, then we basically grabbed our maximum drift that we expected. We say, okay, 2% or 2.5%. We handed it to the non-structural team. Then the non-structural team, they worked with our sponsors and donors to detail those to their best they can to detail those so that they can tolerate that drift. So I think if you are using those details, even if it is not wood, it is a concrete or steel building, you could still have a similar result. I mean, the non-structural will not get that much damage if you're really careful about that.
Yeah. Ludovica is asking whether the PT bars experienced any loss of pretension during the testing.
Okay, yeah. No, the PT, we monitor them very closely. For a PT bar that is about 35 meter long, it is pretty hard to see loss. The only chance you see loss might be the entire wall gets shortened, but over the time of the construction to testing, about let me see, from PT to finally we're done, at least 6 or 7 months. With rain and environmental effect, we don't see any loss. And then when it comes to testing, the wall rocks, but the amount of uplift is so small compared to the 35 meter total length, it just doesn't do anything. In fact, the PT is well below yielding. I think our initial PT is about 40% yielding. Then the maximum measured PT during the dynamic test is only about 55% PT yielding. So you're doing a 40% and 10% up and down, and that's it. So there's no loss. For 2-story, yeah, when we shake it really hard, the last one, yeah, we did yield. We managed to yield PT. So once it yield, it losses. But for this one, it's just geometrically not possible to yield the PT.
And finally, Jishuan asks whether you use DDBD, the direct displacement based design methodology to design, or what methodology did you use for designing this?
DDD was used in the Japanese test, the 7-story one, but not on this. For this one, the methodology is really, there's 2 steps. The first step is actually do a force-based design using a procedure that we developed, which actually I published a paper on that, with a R factor close to 7. So basically, we just follow the SE7, do an R factor of about 7, and then we did a force-based design of the rocking wall. We size all the rods and everything. Then we put that into an OpenSys model, and then we do your typical performance-based, displacement-based design thing. Not a direct displacement design, but a displacement-based design. Basically, it's nonlinear time history simulation and all that. But to our surprise, in fact, for this type of a metal system at this height, the nonlinear time history displacement-based design didn't really alter much of our prescriptive approach. So it turns out that the prescriptive design, force-based, using R about 7 is actually good enough for this building, at least. I mean, I wouldn't say it to work for all the other buildings. We're actually doing that study right now on the P695 approach, but we'll see. Hopefully we'll put a design methodology for this out in SC7 and NDS by 2028. That's a next cycle. So short answer is not a DDD, but it is displacement based. It is based on a nonlinear time history simulation using OpenSys.
So thank you very much, Ling. I just have a short question from my side. I think you have done obviously a very impressive campaign of testing, discipline defining type of test, and you've pushed the boundaries and you've worked with several industrial partners. Mm-hmm. Were there any detail there in terms of construction that was difficult or that the industry was not prepared? And are we ready now to see more of these buildings coming? Do you see any barrier?
Frankly, I mean, sounds pretty cheesy, but no. All the details here, all the connection details, they are actually quite simple, because rocking wall itself, it turns out to be a very simple system. It's simple to analysis, simple to simulate, and it's not that difficult to build. The one challenge we have is the stitching of the wall panels together. We have some trouble because our epoxy rod, those connections are epoxy rods. So basically, you drill the wood on each side, and you put a rod inside, then you inject the epoxy to glue them together. We have some trouble that our hole doesn't line up, but that's a one-time thing. Once we resolve that, in fact, I mentioned there's a subsequent test by Andre Barbosa at OSU. They replaced 2 of the walls, then they did the same detail, but then they did it right, and then it went very smoothly. So there's no particular difficult connection here, and I think and I hope we'll see more of those buildings in the West Coast and around the high seismic region of the world soon. One final insight is that in fact, tall buildings are one of the best in seismic. So don't be afraid to build tall if it's just seismic, right? Of course, you have to do fire and all that, but from seismic standpoint, in fact, I think we should have a height limit for wood buildings. That it's not height limit. You cannot build beyond certain height. Is that you have to build beyond certain height. So because it really helps.
Yeah. Well, thank you very much for a fantastic presentation and a very clear response to all of our questions. There was a lot of engagement, so we are very happy to have had you in this second seminar. So the next seminar is going to be looking at innovative frictional damping devices. That's the next second seminar, and it's going to happen on the 11th of the 6th of 2024. Right? So thank you very much.
Yeah, thank you, everybody. Thanks, Christian. Thank you, Ice. And I'll see you around, I guess.
Yeah.
Bye.
Bye.